Hello everyone. Uh, this video, uh, where right? So what was the date of this video? It was 16th February 2021. So it was from 1 year ago, right? And so last intention, he commented this thing. And yeah, so I just got inspired by this. I made all of this. So what is this question? It's like I as a function of k, so n is some constant, right? So even though I wrote n inside of it, it's supposed to be a constant. So I as a function of k is given by summation from r equal to 0 to n of negative 1 power r and then r power k and cr, right? So yeah, you can always do this. You can define it for any kind of k value, right? I mean, any kind of k value where this thing doesn't actually become some problematic thing, right? So for example, you cannot have k as negative numbers because then 0 power negative number doesn't make any sense, right? And you cannot have k is equal to fractional values because they're negative 1 power fractional values. They don't make sense. So yeah, so for like any positive integer, actually any whole number k, you can define this thing. In fact, you can even define this for negative numbers, just not for 0. You could remove r equal to 0 term because I mean that doesn't actually do anything. So remove that and then you can do it. But whatever. At that time, I defined it like this. So this is how I is defined. And we have to prove that um, this I value is just equal to 0 if k is less than n, and it's equal to negative 1 power n times n factorial if k is equal to n. So first hint that they gave us is this negative 1 power n. Because we have this, what we'll do is that instead of going from r equal to 0 to n, we'll go from n to 0, all right? Um, and n you will just have negative 1 power n, right? So the first term will just have negative 1 power n and then n power k and ncn. So you just take out negative 1 power n from this whole series, right? And that's what I did. I took out the negative 1 power n, and the inside stuff is what we look for, right? Yeah, so I mean, to get the inside stuff, I just did negative 1 power n times all of this. I should have done negative 1 power negative 1, but well, like whatever. It doesn't actually make any difference, right? It's just negative 1. So negative 1 power 2 n, the same thing as negative 1 power 0. So, right, this value is the inside stuff, and we want to know what that value is. So they told us that at n equal to sorry, at k equal to n, you will have this value as n factorial, and at k less than n, you will have 0. Why is that happening? Well, I mean, proved all of this using induction, sure, right? So go watch this video if you want. What's the title of this thing? I don't know. Well, whatever. Yeah, it was like another, yeah, this thing, another binomial theorem trick. So just watch that video if you want to see the induction proof. Now here's the combinatoric proof. So coming to this comment, n is the sorry, n is the total things. So k can't be greater than n. Um, well, yeah. So I think he's talking about combinatorics over here, right? That was the first impression. Then, by the way, you can do this by selecting n different things out of m different objects. So I don't know what m is, right? What kind of m is he talking about? I don't know. In this question, the only two things that we know, right? So only two known things are k and n, right? So depending on those two, this will change. So it's a function of k and n. That's why, right? So r is, it's just a dummy variable. It's just going from 0 to n. It just represents a summation, nothing big. Only k and n are the ones that matter. So I don't know what m is. But yeah, he's talking about combinatorics, and that's why I'm going to think of this thing as some kind of combinatoric number, right? So since we are going the opposite way, right? So we're going to start off at n. So ncn is just 1. So what do you have? Just have so like negative 1 power 2 and like that's just 1, doesn't matter. What you have is just n power x. What does n power x actually mean combinatorically? N power k, well, whatever. So n power k, what does that mean? That this means you have like n distinct places and k distinct objects, and you want to put these objects into those places, right? So the number of ways of doing that would be n power k. And yeah, repetition allowed, so you can put two objects in one place. It's cool. You can, right? So the number of ways of doing that is n power k. Next, the next term will of course be negative, because negative 1 power r, right? So it's an alternate negative positive. And whenever you have something like that, just think about inclusion exclusion principle, because that's what will, yeah, make that happen, right? Negative, alternate negative positive, right? Then in the next term, you have NCN minus 1, which is pretty much the same thing as NC1, or okay, you know what? Yeah, NCN minus 1. NCN minus 1, and then n minus 1 power k. So NCN minus 1 is like you're choosing n minus 1 places out of these n places, right? So once you have chosen those places, you want to put all your distinct objects into those n minus 1 places. But then you are putting a minus in front of that. So it's like saying, so initially you had like n power k, which is all the ways of putting these k objects into the n places, right? Without worrying about any kind of rules. Next, what's happening is NC n minus 1, you can think of it as NC1 as well. And NC1, that represents the number of ways of choosing a place where you don't want to put any object, right? So there are NC1 ways of that. And once you have done that, the other places, so the other n minus 1 places, so those to the power of k, that just represents that you want to put all the objects into those n minus 1 places. So all the ways of doing that. So you can already see what this alternating negative positive was doing, right? It's like, and then go to the next term. So we'll have plus, and then, you know, NC2, and then n minus 2 power k. So it's like you want two places where you don't put anything, and then all the other places you want to put something. But then of course out of these there will be some cases where you are actually not putting anything. So using inclusion exclusion principle, what this actually is like the number of ways of putting these k different objects into these n places, such that every place has at least one object. So for example, if I did this for k equal to n plus 1, right? So the first thing that I would do is, so using inclusion exclusion principle, is first of all, I'll just put these n plus 1, so k equal to n plus 1, all right? So I will just put these n plus 1 objects randomly, right? So that will be like, what, n power n plus 1 ways of doing that, right? Without following any kind of restrictions or whatever. Then I'll break one restriction. So I'll break the restriction that, so yeah, the rule I'm breaking is like one of them doesn't have any object in it anymore, right? So that's what I'm breaking. Does that make sense? If you know the inclusion exclusion principle, you will understand what I'm saying, all right? So number of ways of breaking that rule is what? It will be, well, what's the thing? Of course, NC1, right? So NC1 or NC-1, both are the same. So NC1 ways of breaking that rule. And then the remaining n minus 1 places, those will be filled by our n plus 1 objects, right? Yeah, so we just want n minus 1 power n plus 1 and so on. So in the end, this just like basically becomes the number of ways that you can put n plus 1 objects into these n places, such that every place receive at least one object, and all of these n plus 1 objects are distinct, and also the places are distinct. So the number of ways of doing that, what would that be? So instead of having n plus 1 objects, if it was n objects, it's very obvious. It's just n factorial. That's the only way you can do it, right? So the only way is, right, you put one object in every place. That's right. And the number of ways of doing that is of course n factorial, because distinct places, distinct objects, right? So you want like pairing. Does that make sense? So n factorial ways. Now for n plus 1, it's a little different. So for n plus 1, what you could do is, you just, first of all, you just choose the place where you got an extra object. So the number of ways of doing that is just NC1, right? And then once that's done, So like n ways of doing that. Once that's done, those two objects that will be on that place, you choose those. So n plus 1 c2, right? Those ways. Once that is done as well, right? All of the other objects those are remaining. So like n minus 1 objects, you will just insert them the way you can, right? The only way is, of course, one object per place. So n minus 1 factorial. And that's this function. N, ncr, n plus 1, comma 2, which is basically just n plus 1 times n upon 2. So I shouldn't have written it like this thing, but whatever. And then that times n minus 1 factorial. So this number will be the number of ways of doing that thing, right? So inserting n plus 1 objects into our n places such that each place gets at least one object. Now that's the same thing as saying f of n plus 1. So f is a function of k. Okay, I used x over here, but you get the thing, it's a function of k. So pretty much the same thing as I, except it's just a function of k. So n is a constant, right? We are assuming that. Then this is just equal to f of n plus 1, because now the number of objects is, of course, n plus 1. And this, I mean, this just basically explains why it's 0 if k is less than n, because you can't put if your number of objects is less than n, um you can't put every place having one object, right? You can't have that, right? Even if you spread them out evenly, it would not work. It will just not work. And that's why it's 0 if k is less than n. And the first time it's not 0 is when k is equal to n. So, right. I mean, this guy said that k can't be greater than n. That's not right. K can be greater than n. I think it's like he's doing it in some different way, which right now I don't understand. But yeah, he did give me a bit of insight into what I can do. So it can be done combinatorically. But at that time, look, at that time, it was what? What date was it? 16 February 2021. Think about it. An year ago, I would not have known any of this, right? So yeah, I mean, I was not that experienced with it. So now I do, and there we go. You got the thing. So yeah, this is like the little thing that I made. So k equal to 6, 6, at one you just got 0, and then so on. Like yeah, so you got 0, 0, 0, 0, 0, and when it becomes 7, right? It will basically like go out of the graph, although it's not actually going out of the graph. Because f of k, that is 5040. That's why it seems it's out of the graph. In reality, it's not. So, okay, I should just zoom out really, really, really hard, and then I'll be able to see the point. So yeah, this is the way. Okay, where is it? Oh, come on, just keep zooming. Oh yeah, so here it is. So at 7, it's like 5040, and you can see what happened. It went from this to that somehow, right? So yeah, it's kind of a weird thing how this smooth curve gives you this thing, right? I mean, okay, it's actually not that weird because it's based on this, just extended to all real numbers, right? So it's not that weird. And yeah, well, that's all I wanted to say. So, I mean, I only did this for n plus 1 and n, but you could do it for n plus 2 as well, or you could like form a general formula if you can. I don't know how to do that. So that's it. See you guys in the next video. Uh, Wait, is my mouse working or not? Okay, see you in the next video. Oh, come on. Okay, my mouse is not working. Just wait a second. See you guys.